So the pivotal breakthrough that's necessary, that some company has to come up with to make life multiplanetary is a fully and rapidly reusable orbit-class rocket.
Reusable rockets are probably the biggest game changer in modern spaceflight. SpaceX showed the world it was possible, and now everyone is trying to build one. But have you ever wondered how these rockets actually work? What parts get reused, and what happens after they land? Well, today we're diving into some of the most famous reusable rockets and the science behind them. Because even though watching a rocket land feels almost normal these days, making that happen is still an insane engineering achievement. Landing a spacecraft is one of the biggest challenges in space exploration. If you want to bring heavy scientific equipment, or eventually people, to the surface of another planet, at some point you have to actually land the thing. Scientists have been obsessed with solving this problem ever since NASA started planning the moon landings back in the 1960s. Turns out, don't crash is a surprisingly difficult engineering problem. Now, a lot of people don't realize that a rocket booster that lands back on Earth is basically a giant flying robot. Once it begins its trip back, no pilot is sitting inside with a joystick. It's making thousands of decisions completely on its own using onboard computers. And here's where things get really interesting. When a reusable rocket like Falcon 9 or Starship comes in for landing, there isn't just one route it can take. There are literally millions of possible paths from the sky to the landing pad. Programming every single movement ahead of time would be like trying to write turn-by-turn directions for every pebble you might hit while driving. That's not exactly practical. Instead, engineers let the computer solve the problem itself. The flight computer knows three things: where the rocket is starting, where it needs to land, and the rules it has to obey. Things like the laws of physics, engine performance, fuel limits, and structural constraints. Then it mathematically searches through countless possible trajectories and chooses the one that lands safely while using the least fuel, making the smoothest maneuvers, and staying within every limit. It's basically GPS navigation, except instead of avoiding traffic, it's avoiding becoming a very expensive crater. But finding the perfect path is only half the job. The rocket actually has to fly that path in real time, and the real world has a habit of refusing to cooperate. That's where several other systems take over. First comes state estimation, where the rocket constantly figures out exactly where it is by combining data from GPS, inertial measurement units, radar, and other sensors. Then comes closed-loop feedback control, which compares the rocket's actual position to where it should be and makes tiny steering and engine adjustments dozens or even hundreds of times every second. And if something unexpected happens, like a gust of wind pushes the rocket off course, or an engine produces slightly less thrust than expected, the onboard computer doesn't panic. It simply recalculates a better trajectory on the fly and keeps going. Meanwhile, it's also juggling a ridiculous number of other problems. The rocket gets lighter as it burns fuel. Winds change. Engines don't respond instantly. Sensors have small errors. Aerodynamic forces constantly shift. Multiple engines have to work together without producing uneven thrust. And the system still has to be prepared in case something doesn't perform exactly as planned. So landing a rocket isn't just one big math problem that gets solved before launch. It's an endless cycle of sensing, predicting, optimizing, correcting, and controlling. All happening in real time, every fraction of a second, until the rocket gently touches down exactly where it was supposed to. Honestly, it's kind of ridiculous that it works at all. So, how did SpaceX do it? Well, when Elon Musk looked at a Falcon 9 booster, he didn't see something that should be thrown away after one flight. He saw the most expensive part of the entire rocket. So instead of accepting that rockets had to be disposable, SpaceX decided to attempt something most people considered impossible. Launch a rocket vertically, send its payload toward orbit, then bring the booster all the way back under its own power and land it upright, either back at the launch site or on a drone ship floating hundreds of kilometers out in the ocean. But the craziest part is not just landing the rocket. It's landing it with extreme accuracy. Today, Falcon 9 routinely touches down within about 10 meters of the center of its landing pad. Sometimes that landing pad is a drone ship that's literally bobbing around in the middle of the Atlantic. Trying to land on that is a bit like throwing a dart from an airplane onto another airplane, except both are moving. That level of precision didn't happen simply because engineers got better with practice. Every launch generated enormous amounts of flight data. SpaceX fed all of that information back into the design process, constantly improving the software, refining the hardware, tweaking the flight algorithms, and even redesigning parts of the rocket itself. Every mission became another engineering experiment. Once the first stage separates at roughly 70 to 80 kilometers above Earth, the upper stage continues carrying the payload toward orbit. Meanwhile, the booster suddenly has an entirely different mission. It has to fly itself home. Depending on where the payload is headed, it may return to the launch site or aim for an autonomous drone ship waiting far offshore. Either way, no one is remotely flying it. From this point on, the booster is making every decision on its own. The trip home happens in 3 major steps. First comes the boostback burn. Using 3 of its 9 Merlin engines, the booster fires in the opposite direction of travel, slowing itself down and, if necessary, reversing course toward its landing site. Some missions skip this burn entirely, especially when landing on a drone ship that's already positioned downrange. Immediately after stage separation, however, the booster has another problem. It's still pointing the wrong way. To solve that, 8 small cold gas thrusters near the top of the rocket fire bursts of compressed nitrogen gas, rotating the entire vehicle through a dramatic 180-degree flip. Since the rocket is still above most of the atmosphere, there's no air for fins to push against. These tiny thrusters are the only way the booster can control its orientation in the vacuum of space. Throughout the flight, you'll often notice little white puffs as they continuously fine-tune the rocket's attitude. As the booster falls back toward Earth, 4 titanium grid fins unfold near the top of the stage. These strange, waffle-shaped fins actually date back to Soviet missile technology from the 1950s. They're incredibly compact when folded, which makes them perfect for launch, but once deployed, they become remarkably effective steering surfaces. As air rushes through the grid structure, the fins redirect the airflow, allowing the booster to guide itself through the atmosphere with extraordinary precision. They're one of the biggest reasons Falcon 9 can consistently hit a target only a few meters across after falling from the edge of space. Eventually, the rocket reaches the thicker part of Earth's atmosphere. That's when it performs the entry burn. 3 Merlin engines ignite once again, slowing the booster before it slams into the dense lower atmosphere. This dramatically reduces aerodynamic forces and heating, making the rest of the descent much more manageable. Throughout all of this, the rocket never stops thinking. Its onboard computer constantly compares where it is with where it should be. Using its inertial navigation system, which combines gyroscopes and accelerometers, with GPS data, the booster always knows its position, speed, and orientation. If a gust of wind pushes it sideways, if one engine produces slightly different thrust than expected, or if the atmosphere behaves differently than predicted, the computer notices almost instantly and makes corrections in real time. There isn't a human pilot secretly steering it from mission control. The rocket is flying itself. Finally, with less than half a minute remaining, Falcon 9 begins its last maneuver. The landing legs deploy using high-pressure helium, locking into place automatically. Built from carbon fiber and aluminum, they're incredibly lightweight, yet strong enough to support a booster standing over 40 meters tall. They even contain shock absorbers to cushion slightly harder than planned landings. 1, or sometimes 3, Merlin engines reignite for the final time. Unlike most rocket engines, which are only expected to ignite once, the Merlin engine was specifically designed to restart multiple times during a mission. That's an astonishing engineering challenge when you're traveling at supersonic speeds. As the engines throttle down, you'll notice something else happening. The engine nozzles are constantly swiveling. This is called thrust vector control. Instead of always pointing straight downward, hydraulic actuators pivot the engines by a few degrees. That tiny movement changes the direction of the thrust, allowing the booster to pitch, yaw, and roll with incredible precision. In the final few seconds, every system is working together. The engines are gimbaling, the grid fins are making tiny aerodynamic adjustments. The flight computer is processing sensor data hundreds of times every second. The navigation system is updating the rocket's position continuously. Then, almost unbelievably, A machine that was traveling thousands of kilometers per hour just minutes earlier slows to almost exactly zero at the precise instant its legs touch the ground. A crazy engineering achievement that SpaceX has now made routine. Okay, so now we know how SpaceX reuses the first stage of a rocket. But what about the second stage? Has anyone ever managed to recover an entire spacecraft from orbit? Well, yes, sort of. In fact, you've almost certainly heard of it. It was the Space Shuttle. When NASA introduced the shuttle, it was one of the most ambitious engineering projects ever attempted. Remember, the first shuttle flew just 2 decades after humanity's first trip into space. That's like going from the Wright brothers to the Boeing 747 in one generation. NASA wanted a true space truck. Instead of building different vehicles for different jobs, the shuttle was designed to launch military satellites, commercial payloads, scientific experiments, and astronauts, all using the same spacecraft. For a while, the US government was so confident in the shuttle that it adopted a shuttle-first policy, planning to launch almost every American space mission with it. And compared to the capsules that came before it, the shuttle looked like it had arrived from the future. It launched vertically like a rocket, orbited the Earth like a spacecraft, then came home and landed on a runway like an airplane. Even better, most of it was reusable. The orbiter itself was flown again. Its 3 massive main engines were removed, inspected, and reused. Even the 2 giant solid rocket boosters were recovered after every launch. Only the huge orange external fuel tank was sacrificed, burning up during re-entry. Here's how a typical mission worked. At liftoff, the shuttle relied on its 3 main engines and 2 solid rocket boosters to climb out of the atmosphere. About 2 minutes after launch, the boosters ran out of fuel and separated. Instead of crashing into the ocean like most rockets of the time, they deployed parachutes, splashed down in the Atlantic, and were recovered by ships before being refurbished for another flight. Once the shuttle reached space, the empty external fuel tank was no longer needed. It separated and later burned up in Earth's atmosphere. The orbiter then continued the mission using smaller maneuvering thrusters and 2 orbital maneuvering engines to adjust its orbit, rendezvous with a spacecraft, or eventually begin its trip home. This was where the shuttle truly stood apart. Its enormous cargo bay could carry more than 24 metric tons into orbit and bring back roughly half that amount. Astronauts could even work inside the cargo bay, capturing satellites, repairing spacecraft, and assembling structures piece by piece. Without that capability, repairing the Hubble Space Telescope or building the International Space Station would have been almost impossible. Eventually, every mission had to come home. Returning from orbit meant slamming into Earth's atmosphere at around Mach 25. At those speeds, the air in front of the shuttle became so compressed that it heated to incredible temperatures. Thousands of ceramic heat shield tiles and reinforced carbon panels protected the orbiter from burning up. Now, unlike Falcon 9, the shuttle didn't fire its engines during the final descent. Once it was committed to landing, that was it. It became a giant glider. There was no engine available for a go-around, no second attempt, no chance to climb back into the sky if something looked wrong. The commander had exactly 1 opportunity to line up with the runway while descending at over 340 kilometers per hour. Astronauts often described it as flying a brick. If they missed, there wasn't another try. For the 1980s, though, it was an astonishing achievement. So, if NASA already had reusable spacecraft decades ago, why doesn't every modern rocket work the same way? The biggest reason is that today's reusable boosters are trying to save something much more valuable. When the shuttle's solid rocket boosters splashed into the Atlantic, they were mostly empty steel casings. The fuel was already gone. A Falcon 9 booster, on the other hand, still contains 9 precision-built rocket engines, flight computers, sensors, pumps, valves, and delicate electronics worth tens of millions of dollars. Saltwater and high-end electronics don't exactly get along. Imagine throwing your gaming PC into the ocean, fishing it out a few hours later, and expecting it to run perfectly next week. That's basically what SpaceX is trying to avoid. Instead of recovering a waterlogged rocket, they land it gently on solid ground, or on a drone ship, so almost every expensive component stays clean and intact. But there was another problem with the shuttle. It was reusable, just not rapidly reusable. After every landing, NASA couldn't simply refill the tanks and fly again. Engineers practically took the vehicle apart. Every heat shield tile had to be inspected. Every main engine was checked. The computers were tested. The wiring was examined. Hydraulic systems, fuel lines, valves, sensors, and countless other components all had to be verified or replaced if necessary. That might sound excessive, but remember what the shuttle had just survived. A violent launch, the vacuum of space, extreme hot and cold temperatures, and atmospheric re-entry at roughly Mach 25. That's an incredible amount of stress for any vehicle. As engineers like to say, a million things have to go right, but only one thing has to go wrong. That level of caution came at a price. Preparing a space shuttle for another mission typically took 4 to 5 months, required roughly 750,000 hours of work, and involved millions of individual inspection and processing steps. So yes, the shuttle was reusable, just wasn't reusable in the way we think of Falcon 9 today. Now, SpaceX is aiming even higher. Reusing just the first stage isn't enough anymore. The company's next goal is something that has never been achieved before, a fully reusable orbital rocket. And that rocket is called Starship. The Starship launch system has 2 stages, the Super Heavy booster on the bottom and the Starship spacecraft sitting on top. Both are built from stainless steel and powered by liquid methane and liquid oxygen. Together, they can lift more than 150 tons into low Earth orbit, while still being designed to come back and fly again. So how does this giant machine actually come home? First, the Super Heavy booster separates from Starship after a maneuver called hot staging, where the upper stage actually ignites its engines before the 2 vehicles completely separate. The booster then flips around, performs a boostback burn, and flies all the way back to the launch site. As it approaches the ground, it fires a few center Raptor engines to slow itself down before one of the wildest moments in modern engineering happens. Instead of landing on legs, giant mechanical arms on the launch tower, nicknamed Mechazilla, literally catch the booster out of midair. It sounds completely ridiculous, which is probably why so many people laughed at the idea. Then SpaceX actually pulled it off, multiple times. Meanwhile, Starship continues into orbit to deploy satellites, or, eventually, carry astronauts to the Moon and Mars. When its mission is finished, it re-enters Earth's atmosphere belly first, like the world's least aerodynamic skydiver. Thousands of heat shield tiles absorb temperatures hot enough to melt steel, while large flaps steer the vehicle through the atmosphere. Finally, just before reaching the ground, Starship performs its famous landing flip, fires its Raptor engines, and rotates from horizontal to vertical in just a few seconds. Future versions are expected to be caught by the tower just like the booster, although current test flights often end with an ocean splashdown while SpaceX continues refining the system. With Starship V3, the company is pushing even further, with more powerful Raptor 3 engines, upgraded avionics, improved reliability, and faster turnaround between flights. Booster catches are becoming routine. Catching Starship itself is the next major milestone. The ultimate goal isn't just reusability, it's launching, landing, refueling, and flying again so quickly that rockets start behaving less like disposable machines and more like airplanes.